Welcome to this weekly live session. This time we are going to wrap up Module 103. So Module 101, 102, and 103 so far have been providing us with a sort of minimal overview of programming concepts. Okay, we have been dealing with data, variable, values, assignments, stuff like that in 101. 102 was about conditional statement, and then now we're going to deal with iterative statement. So what I want to do in this session is I want to wrap up the module. 90% of what I had to convey is already in the lecture video that you've seen, in the apprenticeship exercise. What I think is missing, what could add actually value to this module is actually trying to link all of those facts, all this knowledge that you have acquired through those through studying that material, to the 5 programming skills that we have been discussing. Okay, debugging, tracing, implementing, etc. Okay, so I'm going to try to do that as usual. I'm going to try to review the skills in a manner that is actually helping you get prepared for the exam, because the exam, as I've mentioned already several times, the exams will be divided in question, each targeted at one of the specific skills. Okay, so this is what we're going to do during the session. Anytime you have a question, don't hesitate to interrupt. Okay, I have to mention also that, as has been the case a few times now, there is a thunderstorm. So if by any chance I lose connection, I will make sure to record the rest of the video and post it, the rest of the session, and post it as a video so that you can still have access to the content. Okay, and I will do so as soon as I can get back access to the net. Alright, so if I get interrupted, don't worry, I will try to reconnect, but if it takes more than, let's say, 10 minutes to reconnect, then probably the connection is not going to come back up. So in that case, I will record a video offline, and I will upload it as soon as possible. Alright, so now that we have made provision for the weather, let's get started. Let's get started with, as we do usually, the designing skill. So there are 2 things I wanted to remind you of. Okay, this is stuff that you have already seen in the material. I just want to kind of help you restructure it, review it, and refresh your memory before you take the exam. There are 2 things that we leverage in design, really. One is building blocks. What I call building blocks is by no way a standard terminology. And another thing that I call patterns. Okay, so let's review real quick what is meant here by building blocks and pattern. Well, building blocks, the same way that when we learn to use if statement, we learn to nest them, and we learn to put them one after the other. Well, we can do the same thing with loops, right? So we can talk about serially arranged loops when you have 2 loops following one another, and nested loops when you have one loop inside another. Okay, and that's pretty much it. So this is generally this is very comforting to students, because they see that if you have 2 loops, if you need to use 2 loops in a programming exercise, there are really just so many ways that you can put them alongside one another. Okay, I refer you back to the conditional statement module 102 video, where we took 2 if statements and we kind of went over all of the possible combinations. Okay, same thing applies here to do. So building blocks are really low level. It's more, in terms of what can I do with my my statement, my programming language statement, like a loop statement. Then we go to designing with patterns. Patterns are a little bit higher level. Okay, the idea of pattern is, for example, do I need to use a counter-controlled loop or a Sentinel controlled loop? That would be a design decision at the pattern level. Okay, so control loop, counter control loop. Sorry, I have a problem with that tonight. Counter control loop and Sentinel control loops are defined in the lecture video, so you know what they are about. The idea is that you need to be able to differentiate when you are going to use one, when you are going to use the other. So there's a few questions. I'm going to go over that as a review again. There are a few questions you have to ask yourself. Okay, one of them is, for example, do we know before to start the loop how many times we need to iterate? And this is really the key question. So before even to make the first iteration, before to do anything in your loop, if you know that you need to display 5 stars on the screen, you need to load 5 images from the disk into your memory, you need to do 10 times a certain task. As soon as you have a clear number like that, counter control loop. There's no hesitation. Okay. Now it's a little bit more difficult when you don't have a counter control loop. So then you look at what kind of condition you are going to need. Okay. So for example, the second type of classic loop is the Sentinel control loop. The question you ask yourself to determine whether you need to use a Sentinel control loop is, are we going to do, and I'm going to write something, whatever it is, okay, the payoff of the loop pretty much, are we going to do some actions until we get a specific value, and that can be get the specific value from the user. The user type -1, and that means I want to quit the program. The user types bye-bye, that means that they want to quit the program. We are reading a file and we reach actually the last bytes of the file where there is a special code that tells us the file is over. We are communicating over the network and we get some data that means communication over. I'm hanging up, okay? So those are special values. Generally, you are reading from the keyboard, from a network connection, from a file, you are reading some data. And that data has an expected valid range, okay? For example, you are reading grades between 0 and 100. And it's a convention that when you get something outside of that range, specifically -1, pretty much, in this example, I mean, that means that the data is finished. So you do not know in advance how many times you're going to iterate. You do not know in advance how much data is going to be provided to you, but you know for sure that when you encounter that value, that means it's over. That's called the Sentinel value. And then there is, you know, the generic case, which is, are we looking for a specific condition? Okay, and this is pretty much a catch-all. If you do not know in advance how many times you iterate, if you are not looking in the data that you are acquiring in your program, if you are not looking for a specific value to mean end of work, then you are in the general case of the loop with a condition that can be just about anything, okay? So these are really the three questions you have to ask yourself. Probably asking yourself those questions in this order is close to optimum, okay? So these are the questions you need to ask yourself to decide what kind of pattern of loop you want to use. But that's not it for pattern. That's not the only patterns that we have talked about. So let me scroll this back up, okay? And let's keep our discussion on patterns for loops going a little bit further. We also talked about early versus late testing, okay? And again, I want to give you a sort of hint here before you take the exam. You know, how do you decide whether the exit condition, the exit test for the loop, is going to be done early or is going to be done late in the body of the loop, okay? So for definition of this term, early and late, I refer you again to the video lecture. But here the question is, how do we decide between the two? And there's one question you need to ask yourself. Should I be able to skip the loop entirely? Okay, what do I mean by this? Well, you have a loop in your program, okay? You reach the loop statement. Do you need to at least execute one time the hold on, chat window comment? I need to address that real quick. If you cannot see the screen sharing, you need to go to the view menu and then select application sharing. That should fix the problem for you because I made sure that screen sharing was enabled when I was preparing the session. So let me know if that works out. If not, that means we have a technical problem. So again, view menu in Blackboard Collaborate, and then you select application sharing. Okay, perfect. All right. Well, it's pretty important to be able to see those that screen sharing. Otherwise, it's going to be weird to follow. So, okay, I was just specifying the question here that you need to ask yourself when you want to decide between early and late testing. So there are three questions to go through to decide between counter control, Sentinel control. Now, early and late testing, the only issue is when you do an early testing, when you start your loop body, by looking whether you need to stop or not. You give yourself an opportunity to stop immediately. If the condition is met to exit the loop, then you just enter the loop and you test and you get out of the loop. So you never execute the body of the loop. Never. 0 times. Now, if you do late testing, because you make this test to determine whether you should stop looping or not at the end of the body of the loop, obviously you're going to have to go through the body of the loop at least once. Okay? So this is the only difference between early test strategy and late test strategy. Early test mean I may not do anything inside the body of the loop at all, or I may repeat it n times. And the late testing strategy says I will do it at least 1 time, and then I may repeat it up to n time, whatever n is going to be. Okay? So that one is easier generally to get through. We have a very I'm going to talk a little bit about that in the refactoring, but Raptor has a way to do loops that is non-conventional. So we have actually a very powerful, very expressive loop statement in Raptor. We are going to see that when we switch to Java, which we are doing with module 201 this week, then we are going to have different loop statement, each to implement variants of what Raptor can do, namely early test, late test, and stuff like that. Okay? Now there is a last pattern, and this one was not really detailed in the lecture video, so this is going to add a little bit to the lecture video. The last pattern is a loop with, and I said in my note, 2 exit conditions, but let's just generalize and say multiple exit conditions. What do I mean by loop with multiple exit condition? Well, let's say that we have a loop statement. I'm going to write pseudocode, okay? I have a loop statement. I do a little bit of work here, okay? Then I say exit when, which is my conditional in the loop, my test to exit the loop, okay? Exit when, and I say, let's say that we are implementing a guess the number game, okay? So I keep asking the user, give me a number, and I'm going to tell you if this is a magic number that I thought about or not, okay? So exit when the guess provided by the user is equal to the secret number, okay? So that would be one condition to exit the loop. I stop asking for new guesses when the user has found the secret number, the magic number. Or when number of attempts is greater than, let's say, 5. So I'm going to allow this user to guess 5 times, okay, what is the secret number. So I have a loop. I don't want that loop to iterate more than 5 times, so I have a counter number of attempts. I'm going to increment it. It starts at 0, it keeps incrementing, etc. And then I have like a variable guess, which is read by the user, and then a variable secret, which I determine, when my program starts, a random number, for example. And that's it. And this is my end loop. Okay, so I'm not giving you the detail of the code. We're going to come back on that later. We are going to use that example a few times. But what is important here is that in this loop, you have actually 2 conditions. You have 2 ways to break out of the loop. You may break out of the loop when the secret number has been guessed. You may break out of the loop when the number of maximum allowed attempts has been exhausted. Okay? So that constitutes a pattern. Okay, I'm going to move things around a little bit on the screen because I need more room here. So let me take this and paste it elsewhere, so we have a little bit more room here. This requires this leads to a pattern. This requires a little bit more work, because when you exit the loop, when you are after the loop, when you're done with your loop, you do not know why you exited the loop. It's possible that you are there after just 1 iteration because the user guessed right immediately. It's possible that you reach this point here in the code after not guessing the number and exhausting all your possible attempts. So the pattern that is usually employed here is that you have this loop with multiple exit conditions, and after the loop you will find if statements, one or several if statements, that are going to try to determine why you exited the loop. For example, if guess equals secret, okay, then I'm going to do something here. Display, congratulations, you found the secret number in n attempts, for example. Okay? Else, if NB attempts greater than 5, then I'm sorry, you could not find the number within 5 attempts, you know, better luck next time, so on and so forth, okay? And that's it. So you have a, a sort of, okay, sorry, sneeze. You have a sort of pseudocode here that gives you an outline of that pattern, and it can be used for a lot of things. It can be used for, you know, guessing the secret number and having a limited number of attempts. I'll show you an example that was actually submitted by a student this semester, where we try to improve a little the program of blackjack, and we use the same pattern, but we don't have a secret number. We have a target number for our hand of card to reach, which is towards the number 21, and then we don't have a number of attempts, but we have a maximum hand size. Once we have been asking for 5 cards, we are done if we could not reach 21. Okay, so it's really what makes this a pattern, is that this is a sort of recipe. This is a rule that you follow that shows you how to solve an entire category of problems. And we like those things in design, because when we are trying to come up with ideas about how to design our program, we look at the requirement and we try to match the micro features that we extract from the requirement to either building blocks, okay, so that would be the stuff here at the bottom right of the slide, either as building blocks or as pattern, like the different patterns that I've been talking about so far. Okay, counter control versus Sentinel control, early versus late testing, and then loop with multiple exit condition. So it's important that you understand those patterns, that you learn to pretty much master them. Okay, and this is what the exercises are good for. The exercises are going to give you opportunities to see those patterns being applied. Okay, and then this is how you're going to build your repertoire of pattern and be able to better and better identify what patterns you need. Okay, so all right, so this is designing, and I think I'm done pretty much with designing. Yeah, I think we have a good example there. All right, so let's move to implementing. Implementing, relatively easy, I told you, okay, but I have still one thing here to specify that I think would be interesting for to help you get ready for the exam. What I have here, I have different requirements, all right? And the question I'm trying to address is whether I'm going to use late or early test, okay, to implement the loop that those requirements call for, and what is the condition I'm going to use, okay? What is the Raptor loop exit condition that I'm going to use to implement this? So these 4 different requirements are 4 different versions of the same thing, very, very similar to one another. Let's take a look. I'm asked to initialize the value of an integer variable named n to 0. So assignment statement, n is assigned 0. Then display it, display the value of n, and increment it, increment the value of n by 1. So we're talking about a put statement followed by an assignment statement where n is assigned n plus 1. We've done that in exercise, okay? Until it reaches the value 11. So every time you see in the requirement keywords like while, until, repeat n times, okay? I'm not using it in this example, but all of those English expressions should strongly suggest to you that we are going to use a loop. Okay, so in the case of this first requirement, what is interesting is that the requirement says that we initialize a variable, then we display it, then we increment it, and then until we worry about what condition we need to satisfy to stop looping. Okay, so is it going to be late testing or early testing? Any idea, any suggestion? Early testing. Okay, let's figure it out. I mean, we have to get a method, right, to figure out whether we're right or wrong with those things. So my gut tells me that this is early testing. Let's figure out what's happening here. So I'm going to write some pseudocode on the side, okay? Initialize the value of an integer variable n to 0. So n is assigned 0. I'm trying to use a notation that's really similar to Raptor, okay? Then display it. Okay, so put n. Alright, then increment it by 1. N is assigned n plus 1 until, so okay, I'm going to think a minute about how I implement this. So right now I just write until it, meaning n, reaches the value 11, until n is equal to 11. Alright, so I know that I need to put my loop somewhere. What is being repeated here? This part. Okay, because it doesn't make sense to initialize, 5 times. You initialize 5 times, it's still the same, it's 0, okay? So I want to loop, I want to display n, I want to increment n, I want to do so until n is 11, and then that would be the end of my loop. Okay, so this is kind of looking like a pseudocode version of what Raptor does. This here, until n equal 11, in Raptor this is exit if or exit when, okay, however you want to interpret that diamond symbol, okay, which is a condition for stopping the loop, exit when n equal 11. So the idea that the requirement told me to do something, okay, then told me to check whether I should stop doing it over and over and over again at the end, suggests actually late testing. And the only way to figure this out, to verify your intuition, or to just determine it, from scratch, is to try to translate the requirement into loop code. Okay, so that would be actually the first requirement would look something like that, and I already answered the second question, which is what is going to be the Raptor loop exit condition, n equal 11. So in my diamond symbol in Raptor, I would put n equal 11. When n is equal to 11, yes, true, I get out of the loop. Okay, so that's to give you an idea, to help you practice, transforming requirements that are in plain English, okay, into code. So observe that I'm not asking you to design something complicated. You do not have to identify a pattern. You do not have even to identify a building block. Everything is given to you in the requirement. This is an implementation question. It's not a design question. So I give you pretty much a requirement that details everything about the program. Unfortunately, it's written in plain English. So that means that it's a little ambiguous at times, so that means that it's not well structured. So that's what the implementing skill is about, okay? Being able to interpret this plain English description of the program into an actual computer program, formal, unambiguous, nobody can misinterpret what it's doing, and we can execute it on a computer, okay? So part of this is going to have to answer questions such as, do I go for late? Do I go for early tests? What is my Boolean expression? But all of this is already in the text. You just have to extract it, okay? So I hope you see the difference on that example between designing and implementing. Designing, I just give you an idea of my goal, and you figure it out. You figure out if you need a loop, 2 loops, 3 loops, 5 loops, 2 if statements, what order, how they are arranged. All of this is up to you. I don't want to hear about it. I'm not an IT person. I'm not a programmer. Implementing means I am a programmer. I have an idea for a program. I wrote down real quick in pseudocode or in English, what the program needs to do, and I want you to implement it. I want you to code it. But I gave you already the solution. It's just probably not as well specified as a computer program because it's in plain English. All right. So that's one example. Now I choose this example. It's not a summary of every possible English description of a loop you can encounter. But I wanted to take something that I could modify 3 to 4 times, give you small differences every time, and show you how the nuances impact how you want to implement that piece of code. Okay, so let's take a look at the second requirement. Very similar, right? Initialize the value of an integer variable named n to 0, and then you display it, increment it by 1, while it is below the value 11. All right, so let's start with test. Late or early? What do you think? So same idea, okay? You need to take a piece of paper and probably write, the equivalent of this, just so that you can get an idea of, exactly what you need to do there. So we can take this and modify it, for example. Late, yeah, correct. So let's view how we would come up with that conclusion, okay? So initialize value of an integer, blah, blah, blah. Well, that sounds like this is the same thing than before. There you go. My dog is in the background trying to look for a treat, I think. All right, so initialize the value is the same. Then display it. Well, okay, that looks like a but statement again. Okay. Then increment it by 1. That looks again like the same thing. So far we are doing the same. Okay. Then the difference here is we use until it reaches the value 11, and now we use while it is below the value 11. So these are equivalent statements, right? I'm going to keep doing something until I reach 11. And then I'm going to keep doing something while I am below 11, okay? All right. Well, so what would be the condition here? Okay, we have established already that we are going to use a late test, okay? Now, what is the condition that, that we should use here? Any idea? Not sure? Well, it's a little bit tricky here because what we want to implement is while the value of n is below the value 11. That's what we want to implement. But we don't have like a while statement. When we work in Java, we have a while statement, so we can implement that straightforward. In Raptor, remember that the Raptor condition is actually an exit condition. It tells you when to get out of the loop. So the while word in English gives you a condition which, as long as this condition is true, you keep doing things. Okay? I'm going to keep waiting here while it rains. So as long as it rains, while raining is true, I keep waiting here. Okay? So we have to inverse things. Okay? The exit condition for the loop, if we need to continue looping while this is true, then we need to exit when this is false, which means, you know, return equal to 11. Okay? All right. So this is a little bit tricky here. You see that sometimes you do not express in plain English things the same way that you express them in your programming language. So that's why I took this example. You have to be aware that words like until, while, repeat n times, all of these imply that you're going to use a loop. But the specific words that you are using in plain English have consequence on how you implement that loop. Okay? So again, we're not doing any design, we're just doing implementation, but it has its own challenges, right, as you can see. Let's take a look at the third one. Initialize, ooh, this is the same thing again. Then, while it is below the value 11. All right, so here's what's happening here. We are using the while. So that tells me that we are going to use, you know, the same condition here. Because we express our condition with a while, but really in Raptor we need an exit condition. When do we stop? So I'll do this conversion. Okay, I'm going to use the same. Now, the interesting thing is that the way it's returned, the way the requirement is written in plain English, it tells me that first I initialize, then it gives me the condition. Okay, so in my little pseudocode here, I have figured out that the exit when condition would be death. It's handled right away. Okay, I initialize, and then I'm told exactly when I'm going to stop. So I test whether I'm going to stop here. And then the rest of the requirement, you know, by now it's getting to be, I hope, you know, clearer. It's going to be a button, an increment n, and this is going to be what I want to repeat. So this, the position of the while or until keyword in the description of the program influences greatly, you know, what the author of the requirement wants you to do, when they want you to check actually whether it's time to stop looping or not. So bottom line, we are in for an early loop here. Okay, and the last one was going to be relatively easy now that we have seen, you know, all those patterns. The only difference is The while has been replaced by until. But the until is still early in the loop, so no doubt here that I'm using early. What about the condition? Well, I'm using until, so I go back to the first requirement example, sorry about that, which tells me pretty much that my condition is going to be n equal to 11. So, does that make sense? Those four examples, do they make sense? Do you have any question about them? As I said, it's not exhaustive. It's not all possible English sentences that can, talk about a loop. I don't think that would do us much good to try to generate a million sentences like that. But the examples are different enough and subtly different enough that I hope they give you a good idea of, the challenge in implementing. And that's really what I'm aiming for here. I see someone is typing a question, so I'm just waiting to see if I can address it. All right, quick question in the chat window. Yes, to confirm, the words while and until appear after the word then, suggests an early test. Yes, and I use the word then in this requirement to emphasize, the sequential aspect. First, initialize your variable, then do this. So there's no doubt, no ambiguity. Now, to be honest, real requirement, especially the early version of your requirement, will be probably less clear than that. Okay, so that means that even with good definition of what the solution is, it's sometimes difficult to implement it. This happens also with research papers. Sometimes people explain in a research paper the algorithm that they design. Unfortunately, they use pseudocode, they use plain English. They don't necessarily provide the code every time, directly. And this open up possibilities for interpretation. And when you try to replicate the results, sometimes you find yourself asking yourself, well, what did they mean exactly here? Okay, that happens occasionally. So that just shows that even if you have the solution to a problem, you have the program explained to you, it still takes some work sometimes to go from this explanation, to the real program that actually works. All right. I think this is everything I wanted to cover for implementation. Let me double check. Make sure I don't forget anything. No, we're good. All right. So let's move on to tracing. So tracing question with loops are fantastic. There's not that much we can do with the module 101 content. Actually, we can probably have tracing question that emphasize operator precedence. Okay, operators associativity maybe, maybe rounding up, like the integer division and stuff like that. But then again, Raptor does all those things in a way that makes it really difficult to make errors. So my point is that tracing for module 101 was relatively trivial. With module 102 and the conditional statement, now we got into, different flow of execution in the code. Well, with loop statement, we also have different flow of execution in the code. Okay, we can. The key question with a loop is how many times are we going to iterate? It's a key question when tracing. It's also a key question if you do, more theoretical computer science and algorithm analysis. Okay, you have a loop. You want to know how many times the code inside the loop will be executed, and it can be anything from 0 times, you skip entirely the loop, to n times, n being either known in advance, so we are dealing with counter control loops, or being just the number of time it takes us to reach, the Sentinel value or whatnot. So what I have here is a typical Well, actually, it's not formatted exactly as a tracing question because I'm not asking you to fill, line per line each step of execution, but it's more an example of a typical tracing program, a program for a tracing question. So here's a simple loop, counter control loop. I start n at 0. N is my loop index. I loop this part of the code. This part of the code simply increments n by 7. And then I'm going to exit this loop when n is greater than 70. And after the loop, I display, after the loop, n is and the value of n. Okay? So I have a very simple program here. It's in line with what we've seen in the lecture video. It's probably simpler than most of the apprenticeship exercise and practice exercise. Okay? So let's use this little program that's kind of an archetype of a counter control loop to reflect on what can happen when you trace. Okay? So instead of demonstrating the tracing here, I'm going to make you think a little bit about what happens when we turn the little knobs that are available to configure a loop. Okay? And there are just a few things that really matter in a loop. The initialization value matters. What is it? The initialization value is the value that we set inside of n before to start the loop. Okay? So counter control loop, you always have a counter loop, a counter variable, like in this case it's n. And you always have to initialize it before to start your loop. Okay, that's part of the counter control loop pattern. So here I choose to initialize n to 0. So it's a decision. You can, if you want to repeat n times, you can start counting at 0. You can start counting at 1, -5, 73, whatever you want. Okay, if your goal is only to repeat a certain number of iterations, you could iterate 10 times with n from 73 to 83. That would just work fine. Okay, the obvious question is why complicate your life like this? But there are situations where you need to do that. Okay, so here the first question is, what do we initialize n to? And in this case, 0. Then the second question is, are we using early or late testing? So we are going to start, regardless of what this example shows here, we are going to start by considering early testing. And I'm going to show you the Raptor diagram, and we're going to play with it, modify it, so that you can see. So I'm just following a preset order here. And then what is my condition, my loop exit condition? In this case, I'm going to start with n greater than 70. And my question is, what is going to be displayed by the program here, okay, in the but statement after the end of the loop? So let's cheat a little, okay? We are going to use Raptor. So I implemented a version of this program. Let me double check that it matches our test here. Initialization is 0. I want an early test, so I want this assignment statement to be here after the test. Early test in the loop, okay? The test is n greater than 70. All right? So if you are looking for getting some practice in tracing loop, this little program here, it's very simple. You can implement it in literally 2 minutes. Try to trace each of the cases here that we are going to show on this slide. Trace them by hand, okay, making the table where you say, well, this is step 1, then step 2, n is equal to 0, then step 3, I enter the loop, step 4, I test, blah, blah, blah. You know, you've seen example of tracing. So I'm going to give you the answers here, and we are going to discuss if you have any question. I want to stress out here a high-level view, which is how the end outcome can vary based on those parameters, or I can stay the same, depending on how you modify the parameter. Now, once you understand this, then you can go in and, pretty much do the detailed trace for the examples, the scenario that are particularly difficult for you to understand, or that you're not sure exactly you see why we get this outcome. And that will give you an excellent practice for the exam, okay? So let's run this thing here. I run this version of the program, this first version of the program. It tells me output is 77. Okay, so let's take a minute here and take a look at the logic, okay? The logic of the program, if I can get it back here, there we go. The logic of the program is I'm starting with n equals 0. Okay, so I'm going to trace it, I'm going to write it on a piece of paper. Step 1, n equals 0, blah, blah, blah. Okay, I enter the loop. I test immediately if n is greater than 70. Greater strict, not greater or equal. Well, it's false. N is 0. So I get in, and now n is 7. So I start my second iteration, so iteration number 2 of my loop, Iteration number 1, I start with n equals 0. Iteration number 2, I start with n equals 7. Okay? And as you write your trace, you are going to realize that iteration number 3 starts with n14, iteration number 4 starts with n equal to 21, iteration number 5 has n equal to 28, iteration number 6 has n equal to 35, and so on and so forth. Okay? At every iteration, I increment n by 7. Okay? So I'm going to reach at some point n equals 70. Okay, because every number is a multiple of 7. I add 7, so 7, 14, 21, 28, 55, 42, 49, 56, 63, 70. Okay, so after a few iterations, I reach 70. But what happens in my condition? I test. Is 70 greater strict than 70? No. It's equal. It's not greater, it's equal. So this condition is going to be false. And I'm going to increment n one more time by 7, thus leading me to 77. And then the next time I go back in the loop, I test, is 77 greater than 70? Yes, I get out of my loop. The point here is that if you take a quick look at this loop, okay, I start at 0, I increment by 7, am I going to reach 70? Obviously, you are going to jump to conclusions. Not necessarily, okay, but most of the time, people jump to conclusion and they say, well, I understand what this loop is doing. It's starting at 0, incrementing by 7. After 10 iterations, I'm going to reach 70. I'm out of the loop. You are overlooking the tiny little details where the bugs are going to fester. Okay, that's why when I was talking about the tracing skill, I was saying you really need to actually be rigorous. You really need to do what the machine does and not what you think your program does. Very important, okay, tracing. And you can see in this example how it works out, okay? It's very, very common for novice programmers to take a quick look at this program and, you know, say, I don't need to trace it. I'm not going to waste 5 minutes tracing. I know what it's doing. And they are wrong most of the time, okay? So be careful. The greater than sign here in the condition changes the behavior of the program. So what we are going to do is we are going to keep initializing to 0. We are going to keep an early test. But now we are going to replace our condition by n greater or equal to 70. I want to show you how that impacts, okay, the behavior of the program. So if I go in there we go. It's opening the pop-up out of the screen, but let me drag it back in. I do n greater or equal to 70. There we go. And I run this program. Now it's telling me the value after the loop is 70. Okay? If you understood my previous explanation, my previous trace, you are probably on track here to understand this one. You start with n equals 0, so first iteration n is 0. Then it's 7, 14, 21, 28, 35, 42, 49, 56, 63, 70. Finally, we reach 70. After that many iterations, 10 iterations should be, we reach 70. So now, let me go back to Raptor. Now that I have n equals 70, I test this condition, this exit condition, and guess what? n, 70, is greater or equal to 70. Absolutely. So I can get out of my loop. And I get out of my loop one time before the previous example. So this is what, when I mentioned in the lecture, off by one errors. Off by one errors, we're going to just talk briefly about them again in debugging. They are so common, they're so classic. It's so easy to be off by one, okay? So if your goal here was to iterate, you know, until n equals 70 and exactly 70 to exit the loop with n equals 70, you can see how changing the sign of the comparison here is going to do that for you. It's going to either make you off by one, so that would be a bug right here, or it's going to make you hit your target. Third possibility, I want to try to be exhaustive, okay? I like trying to go through some example in an exhaustive manner so that you have a complete overview of a small canonical example. And then from this, from what you learn with the simple example, you can extrapolate to other scenario. Okay, you can extrapolate to other situation. But I want to pretty much anticipate all of your questions by not leaving any special case in the shadow, letting you wonder what would happen if n equals 70. So I'm going to get rid of all of those cases, you know, right now during the live session, so that if something is really weird, you can interrupt, and ask questions. So I'm going to modify again the loop condition, and this time I'm setting n to 70. Let's run. Let's see what happens. Everything is the same. Initialization to 0, early test, and the outcome is 70. Why? Because n takes the value 70. At some point, n will have exactly the value 70. So whether we test equal to 70 or greater or equal to 70, we will get out of the loop. Now that is interesting. Keep that in the corner of your mind, because this is going to be also a great source of bugs. Okay, so I'm going to go back on this kind of example. Literally, is equal, equivalent to greater or equal in a loop exit condition. Okay, we're going to talk about that in the refactoring and debugging section. But for now, because of the way the loop is constructed, because of what it does, you start at 0, increment by 7, blah blah blah. Those two guys are actually strictly equivalent. Okay. All right. Okay. So I went into a lot of detail for those 3 examples. Now what I'm going to do is just to try not to bore you. I'm going to go a little faster with the next 3 examples, okay? But I don't want to go too fast, so I'm assuming you're okay with what we discussed. If it's still a little hazy, just interrupt me. Ask me a question, okay? I don't want to speed through those 3 next examples if you guys have still questions about, why exactly things are happening. I'm trying to not bore you, but at the same time, I do not want to cause you to miss on important material. So we are going to do 3 other tests. And yes, question in the chat window, am I recording the session? Absolutely. I am recording the session. So if you miss the beginning, you'll be able to catch up on the recording, no problem. You're welcome, no problem. So we are going to do 3 more tests. We're going to use that program 3 more times, okay? But this time, we keep our initialization to 0. We just want the test in the loop to be a late test. So late test means the test happens at the end of the loop, okay? So same program, same job. I just moved pretty much, my assignment to the beginning of the loop. Well, we have already n equals 10 here in the program, so let's run it with this. The output is 70. N equals 10. What did I write? N equals 10. N equals 70. Sorry. So the output here is 70. Okay, fair enough. I'm going back to Raptor. I'm going to edit the condition. So it opens it off screen, but trust me, I'm going to edit it to be greater or equal to 70. Okay, you're going to see the result in the flowchart. There we go. So now I have greater or equal to 70. I run my program. What does it tell me? It tells me the output is again 70. Okay, very good. All right, so those 2 are equivalent. They were equivalent before. Okay, so moving from an early to a late test didn't impact this aspect of the behavior of my program. And then I have 1 more test to do. Okay, so I go here, and I'm going to use greater than 70, greater strict than 70. And I run this, and guess what? 77. Okay, so the same logic here. So don't go out and conclude that every early test loop is equivalent to every late test loop. No, it's not that easy, unfortunately. I'm not trying to derive some sort of grand theorem, of what a loop does. If we had access to that kind of, knowledge, then we would be much better at anticipating bugs and anticipating what's happening, in program without having to analyze them in detail. No. This is just the scope of my conclusions are limited to this examples. Okay, this example, sorry. I'm just telling you that in that specific example, because we only do one thing in the body of the loop, which is incrementing n by 7, and because of everything that makes this program exactly this program and not another one, this is the output that I get. Okay, so I'm not going to try to generalize, to all possible loops and stuff like that. But I want to draw your attention to what kind of knobs we have that we can tune, that we can turn to configure our loop, okay? So each of those knobs is pretty much a question that you're going to ask yourself when you try to write your counter control loop. Do I start at 0? Do I start at 1? Go for early or late test? What is my condition? What are the possible conditions? Which one should I take? So it's going to just give you an overview of what happened in that specific case and show you what is the potential impact of those decisions. So we have done early tests, late tests for an initialization value of 1 guess what? I would like to do early test for I'm going to use the same order, okay, for the condition. So I'm also going to test early for n greater than 70, n greater equal to 70, then I'm going to do n equals 70, and then I'm going to do late testing for the same exact loop exit conditions. Okay, so here I am. I have a nice setup here for testing. Let's get back our Raptor flowchart, okay, and let's implement. So we are going to start with late because I have already the late condition here. I have already n greater than 70, okay. The only difference is that here I want to initialize n to 1. So there you go. I modified the assignment. N is initialized to 1. So what's happening? Let's run it. My first result is 71. So this is 71 for this row of my chart. Okay? All right. Next, I'm going to test greater or equal to 70, as I've done before. So there we go. And when you're watching this this video, it's not a bad idea to help you prepare for the exam again, to pause, before I show the result, and to try to guess by hand, to do a trace, to guess by hand, what is going to be the outcome, and then, like play the video. So when you rewatch this video, or those of you who didn't, were not able to attend, when you watch a video for the first time, don't hesitate to rewatch this part a second time and just practice like I just explained, okay? So here, what do we have? I lost track when I was explaining this. So n is initialized to 1. We have a late test. We have n greater or equal to 70, and we get 71 again. That's correct. Last one for that series. The test is n equals 70. Let's modify that. There we go. N equals 70. Run it, and then I get something interesting. What's happening here? The value of n keeps increasing, right? I don't get the output. Where is my pop-up with the output for this loop? It's nowhere to be found. What I'm looking at here is an infinite loop. Okay, I can pause the program. I can reduce the speed at which Raptor goes from statement to statement, and you can see that it is doing something. It is executing. Okay, it keeps executing those loop statements, but it's never ending. Currently, my value for n is 255,697, 704 now, blah, blah, blah. It keeps incrementing. I'm far from 70. So that means that I skipped over 70. At some point, n was equal to, well, let's say 1 as the first iteration. Second iteration, it was 8. Then it was 15. Then it was 22, 29, 36, 43, 50, 57, 64, 71. What happened here? I went from n equals 64 to n equals 71. I was never at n equal 70. So in this case, there is a big difference between testing n equals 70 and n greater or equal to 70. Greater or equal to 70 allows me to stop as soon as n reaches the value 71. Again, do the trace by hand to see what I'm explaining right now, concretely for yourself. But if I have equal, I skip over the value, and guess what? Once I am over the value, I can keep incrementing n. It's never going to be equal to 70. That's exactly what is happening here. So I'm going to stop the program, okay, run halted. It didn't display anything because it never reached actually the part of the program where we display something. It has been stuck here forever, and I had to stop it brutally because it was going to be stuck there forever. So, all right, what do I have here? I have an infinite loop. All right, so that's interesting. That's different. Now let's go back and modify again our Raptor flowchart. We are going to go back to a test early. Okay, these are the 3 cases we have left. We are going to start with n equal. Let's start with actually n. The first one is greater than 70. We're going to do them in order. So n greater than 70. Late test initialized to 1. Let's run it. 71. Okay, so that's fine. That's nice. Get an answer. And then what? And then we are going to go to changing the condition to n greater or equal to 70. All right. Let's run this. 71. Very good. Okay, so far so good. Okay, good results, friendly results. And then the last test we have is n equals 70. And you guessed it. Okay, this time we are testing just n equals 70 to stop. But the problem is that every time we start at 1, okay, when we started at 0, our value for n was 0 at the first iteration. Now it's 1. When we started at 0, at the second iteration, the value of n was 7. Now it's 8. So we are off by 1. So whereas by the 10th or so iteration, we reach the value 70 with our initialization to 0 version, now that we initialize n to 1, we do not reach 70, we reach 71. So we skip over 70. So same problem is happening here than for the late loop. And again, don't go, deducing that every early testing loop is equivalent to every late testing loop. Now, I'll show you an example in the rest of the session where it's not the case. But right now, I'm just pointing out, these specific problems that we are going to recap again when we talk about debugging. All right, so that was that's the wrap up for tracing. Okay, so it's interesting. It's really something that I recommend that you rewatch. Okay, take the time to rewatch just the segment of the video. Make sure that you understand the result in each of those possible scenarios. Even more so, understanding the result is easy because we have a natural tendency to accept this kind of knowledge. But even more so, try to retrieve those results, okay, by tracing. So that's excellent practice exercise for you to trace before you take the exam, okay? If you're capable to go through all those scenarios and come up with the correct result, there's a high probability that your tracing skills are up to par, okay, that you're ready actually. All right, so let's move to the next topic that we usually cover in those weekly live sessions, testing. So we talked essentially about two different things when we talked about testing. We talked about our concern to obtain full code coverage, okay? Meaning that every piece of the code should be executed. And you remember how with if statement, because of the nature of an if statement only executes one of the branch, the then branch or the else branch. Well, that poses a problem because that means that we need to test values in our program that will trigger both branches. We cannot leave any dead code that has never been run while we were testing our program because we just don't know if it works, okay? Same thing with loops. With loops, the situation is a little simpler. What can happen for a loop? Where can we find dead code? We can find dead code in a loop only if we never enter the loop, okay? So there are two possibilities. One, I never execute the body of the loop. Two, I execute one or n time the body of the loop. So first possibility, never execute the body of the loop. Second possibility, execute it at least one time. Okay, and I don't care how many times after that. Okay. Well, that's pretty much it for code coverage. Okay, that's our main concern with loops and code coverage. Now, never executing the body of the loop, when is it relevant? It's relevant when we have test early loops. So see why I was saying don't go and assume because of the previous example that all test early loop behave the same way than test late loop. No, there is a fundamental difference. A test early loop might never execute the body of the loop because we enter, we check immediately if we need to exit, and guess what? If the condition is met, we exit. Whereas a test late loop is going to guarantee us that we are going to at least execute one time the body of the loop before to wonder if we should stop. Okay? So when you have test late loops, you are going to always trigger the body of the loop at least one. When you have test early loops, it might not be so. There are two possibilities. You get out of the loop immediately, and therefore you never execute the body, not even once, or you at least execute it once. Okay, so that's it for code coverage. You see the parallel. We already acquired that concept, with if statement. Now we are adapting it to loops. What about boundary testing? We talked about boundary testing, and we used a lot of, variables that had a valid range, and we wanted to test our program to make sure that it was handling variables that were out of the valid range, stuff like that. Well, here I would like to draw your attention to a variant of boundary testing. When you have a loop, you have, not necessarily in every type of loop, but in some type of loops, you are going to have a minimum number of iterations and a maximum number of iterations. Okay? Let's say that we are implementing one of those guess the secret number games. Okay? The program generates a random number and it tells you guess my number, and you enter 25 and it says too big. You enter 20, it says too small. You enter 22, it tells you congratulations, you won. Okay? That's guess the number game, right? In that kind of program, we are going to have a loop. And as I already hinted at sooner when we were talking about implementing, your loop is going to test two things: whether you found out the secret number, your guess was right, or whether you actually exceeded the maximum number of allowed attempts. Okay, I don't want you to go on forever. I tell you, if you don't guess right after 10 attempts, you lose. Okay, that's the game. So in this kind of situation, it's interesting because you have a sort of boundary value here. And the boundary value is the number of iterations. So it's not like what we did before with boundary value for variables, okay? It's a little different, but it's the same concept. We try to stress our loop, okay? We try to test our loop in extreme situations. What is possibly the minimal amount of iteration I can do? Well, in the guess the number game, that would mean that you ask one guess value from your user, and this user is very lucky, they guessed right, the first time, so the minimum number of iteration would be 1, okay? So I need to construct a test that is going to cause my loop to run one time. So I would, execute my guess the number program, and I would have a test where I enter the secret number right away, and the program tells me, congratulations, you won, and there was only one iteration. I tested this path through my program. Now, what is the maximum number of iterations? In this game, in this example, we have the maximum number of iterations. If I program the game so that you cannot have more than, let's say, 5 guesses, well, then 5 is the maximum number of time I should iterate, right? So this is exactly what I'm talking about here. If your problem, and not all programs allow you to do so, but if your program allows you to identify a minimum and a maximum number of iterations for a loop, you need to make sure that your tests are going to include, your list of tests is going to include one test that makes the loop iterate the minimum amount of time, and one test that makes it iterate the maximum number of time. Okay? That's the concept of boundary testing. If we have 2 limits, we need to test the behavior of our program at both limits. Okay? Is there any way for my loop to never execute at all? Well, if it's not necessarily, probably not. Is there any way for my loop to go beyond 5 trials? Well, I can try. It could be one of my tests, but it should not work. It should never happen with the program. Okay? So that's where the idea of boundary testing comes in. It's a little different than what we discussed before. It's really about boundary testing the number of iterations of a loop. And again, not every loop will allow you to do that. A Sentinel control loop, well, that's not really the same type of situation, okay? But some are going to allow you to do this. So you have to identify whether your program allows you or do not allow you to do some sort of boundary testing like that on the number of iterations. And if so, then you need to write tests to that end. Last concept I want to discuss for testing. When you have a simple Boolean expression, and we used a lot of them, we used if statement with a simple Boolean expression, we used loops with a simple Boolean expression. What do I call a simple Boolean expression? A Boolean expression with one term. For example, n equals 70. Okay, that's just one term. Now, as soon as you start introducing logical operators like AND, OR, exclusive OR, okay, as soon as you introduce those logical operators, you are going to have multiple terms in your Boolean expression. A quick remark I want to bring to your attention here is that when you have multiple terms like that in a Boolean condition, whether it's for if statement or whether it's for a loop statement, either way, you need to make sure that your test trigger all possible combination of true and false for those terms. We did a lot of that last week. Okay, we used those pseudo truth tables, you know, where we had, okay, we have this many conditions, they can be true, false. We listed all possibilities. Then we figure out value for the variable that trigger each condition. Well, that is important for if statement. It's important also for loop statement. Okay, to give you an idea of that, there is a little program that was actually suggested by a student this semester. It's a blackjack program. If you go to the website for the course, you go to practice exercise. I've added it. I've added it very recently because we were emailing back and forth with that student. So I just added it maybe like yesterday. I don't remember. Yeah, something like that. So it's not a problem if you didn't do it. But if you didn't do it yet and you still want a little bit of practice, try it out, okay? The interesting thing with this program, and I'm going to actually show you a base version of it, the interesting thing with this program is that it shows a different example than the guess the number game I've been using so far. That still has exactly the same type of problem. So just to give you an overview here, this is an expansion of the idea of blackjack or not, which was a practice exercise from our previous module. Okay. This time we don't want to just guess whether we have reached blackjack or not. We want to simulate a program that is actually drawing cards until they reach blackjack, or they go over 21. So they reach 21 exactly, or they go over 21. Or they have drawn 5 cards, and when you draw 5 cards, you are done. Okay, that's the maximum number of cards allowed. So we want to simulate a program that's going to just draw cards like that, you know, and pretty much do this job. So what I have here, I have a variable total, which is actually the total points in my hand of cards. Okay. I have a variable hand size, which tells me how many cards I'm holding. So when the game starts, I'm holding 0 card, and they total 0 points, which makes sense. And then in my loop, I do a test early, and I say if my total is greater or equal to 21. If I am at 21, or I blew it and I went past 21, or my hand size is greater than 5, so I drew already my maximum number of cards, then I get out of the loop. And then I display, after I'm done, the loop ended with my total number of points, my hand size, okay, just to let me know if I won or not. And then inside the body of the loop, I do here, I generate a random number, okay, between 1 and 11. And then this is simulating value is pretty much the value of the card I'm drawing. So a card has 1 point, 2 points, 3 points, etc. As soon as I drew a card, I tell my hand size that it's 1 more card, so I'm holding 1 more card in my hand. And the total number of points in my hand is now the total I had so far, plus the point value of the card I just drew, okay, right here. Okay, and then just to help me see how the program is working, I'm doing a put statement at every iteration that say, I'm drawing a new card, this is the value of the card, your hand has that many cards, totaling that many points. Okay, so it just helps seeing what's happening. So let's just run this program real quick to see a typical output, okay? Drawing a new card with value 6. Your hand card has now 1 card. Okay, so I just drew my first card, totaling 6 points. Makes sense. Drawing a second card, value 8. My hand has 2 cards, totaling 14 points. Drawing a third card, value 8. My hand has 3 cards, totaling 20 points. And you see how the condition of the loop worked. As soon as I went over 21, I exited the loop and I said, okay, you ended with 22 points and 3 cards in your hand, you lost. Okay? If I keep running this, here's another example, I reach a hand size of 4. I'd still exited because, you know, I went over 21. Third time, it's random, so I'm not going to get exactly the examples I want to show you, but hopefully if I do it 10 times, we're going to cover all examples, right? Interesting example here. This time, I ended with total 21. So I did not exit my loop because I lost. I exited my loop because I won. I reached exactly 21 with 3 cards in my hand, so that was good. So let's see if we can trigger the last possible outcome, which is I lost because I drew 5 cards. Okay, I drew more than 5 cards actually. So hand size equals 4, 4 equals 3, and there we go, another one where I won. So I lost 2 times, I won this one. run it again. N size equals 4, I reached 29, so I still exited because I went over 21. Exact same thing here. I hope it was different cards. Yeah, different cards, but exact same outcome. I reached 21 in 3 card. Okay, we saw that already. Let me try to trigger. There we go. I went through like examples that we already saw, pretty quick. But what I have now is a total of 24 with a hand size equal to 6. So I was trying to actually get my next card. Okay. So it's just a little example, okay? There's a lot that could be improved in this program, actually. But the idea is that this gives you a way to take a program, that we wrote, with only a statement, see how we can add a loop in there to do something a little bit more interesting. Now, this is not the whole program. This is not the whole program because the assignment asks you actually to display at the end, instead of just displaying your hand size, etc., it asks you to display a message that says whether you won 21 points, or you lost over 21 points, or you lost because you had a hand size that was exceeding its limit. Okay, so that's a very good example as well. That's a good example of a composite Boolean expression here used as a way to exit your loop. And guess what? Every time you have a composite Boolean expression here, you see how we have been testing, right? We have been testing until we triggered all possible ways to get out of the loop. And in this case, there are 2 terms in the Boolean expression. So you could think that there are 2 ways to get out of the loop. And that would be okay. From what I explained so far, that would be the natural thing to think, okay? It's either the left term is true or the right term is true, okay? Well, in reality, there's a little bit more. We know that there are 4 possible true values here, okay? True, 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 false, false, true, false, false. So you need to test for all of those, to account for all of those, okay, in your test. But even more interesting, there's another thing here that is interesting. When I reach the number 21, this condition here is true. But when I reach a number above 21, this condition here is also true. So total greater or equal to 21, when you read it out loud, it even says it. It's greater to 21 or equal to 21. So really, it's like I have 3 terms in this Boolean expression. The greater or equal sign allows me to get out when I am 21 or greater to 21. In this particular game, in this particular exercise, it matters. It matters whether I hit 21 or I hit anything above 21. Okay? So that means that in this part of the code here, I'm going to have to use if statements. Okay, we talked about that pattern, the multiple Boolean terms exit condition pattern. I'm going to have to use a bunch of if statements here to figure out exactly why I got out of the loop and display an appropriate message. But guess what? There are 3 actually different messages I'm going to have to display. One which is you reached 21, congratulations, you won. One that says you went over 21, therefore you lost, and one that says your hand size is past 5, so you lost automatically. Okay? So I just wanted to use this exercise as an illustration. It's a very good exercise to actually add to the other different exercise that we have been talking about so far. So let me go back to where we were. So that was a long parenthesis here for a small bullet item, but we are done with testing. Okay, we are done with trying to recap everything that was in the lecture and apprenticeship exercises regarding testing of loops. The next one is refactoring. So refactoring, again, it's interesting. Let's take another program example here. I have a little program here that I wrote. Okay, I'm going to try to make it a little larger on the screen. Let's take a look first at what the program does. The program tells the user, enter a grade. Enter -1 to end the program. So the assumption is that, I should have written it here, the assumption is that the grade is between 0 and 100. Okay, it's a regular % grade. I initialize the total to 0, I initialize the value for n to 0. Total is going to be the sum of all the grades the user enters. N is going to be the number of grades the user enters. Okay? So my loop is an early test loop. I look for the Sentinel value, so it's a Sentinel control loop. If the user enter -1, I get out of my loop. Okay, and then I look at how many grades were entered. If 0 grades were entered, I'm telling the user I'm not going to divide by 0 because look at what I do if n is not 0. I give the average value of the grade, total divided by n. I tell the user you entered n grades, their average is total divided by n. So to avoid a division by 0, I have this if statement here that allows me to not try to attempt total divided by n if n equals 0. So solid code, foolproof. Also it looks. Inside the loop, n is incremented. Okay, so if the grade that you just typed, okay, here, if the grade you just typed here is not actually -1, then I'm going to increment the number of grades. Okay, I just got one more grade. And then I'm going to add it to the total. And just to help me, you know, not to help me, sorry, and just to go to the next iteration, I'm going to read the next grade value. Is this program working? Let's give it a spin. Okay, I run it, I get a pop-up that say enter a grade, -1 to end the program. Well, you know how I like to do boundary testing, right? So I'm going to try to cause this program to fail. So the first thing I think of is, well, what if I don't want to use the program? I started it, but I don't want to enter any grade, -1. You entered no grade, I'm not going to divide by 0. Okay, so far so good. It's doing what, you know, what I expected. So let's test it again. Now I'm going to enter some grade. So I'm going to enter a grade of 20, and I'm going to enter another grade. Sorry about that, the input dialog open on another monitor, of 10. So I have a 20, a 10, and then I'm entering -1. Just trust me on that. You enter two grades with a mean of 15. Okay, so it looks like it's working, right? Now let's take a look at the code. So we have a piece of code that's working. It's a great time, you know, to think and do some refactoring. So the only thing really that's bothersome in that code is that there are two statements here that do exactly the same thing. So let's say that I go in there and I realize, you know, that I should have told the user that the grade should be between 0 and 100 inclusive. Okay, so I update this part of the code and I run it. So it tells me enter a grade between 0 and 100 inclusive. So I enter 50. And then the next time it asks me for a grade, it doesn't bother repeating to me 0 and 100. Well, maybe that's a feature. Maybe that's what I wanted to do, right? Not quite. I didn't want to do that. What I wanted to do in this example, I just realized that I should be more specific, and I wanted to update both, but I just forgot that my program was redundant. I forgot that there was another part of the program here that did exactly the same job. So that's why redundancy is bad with program. Okay, you don't want. Imagine that you're working on even just 50,000 lines of code. Okay, and there are like 10 occurrences, 10 parts of the code that do exactly the same thing. You're going to forget to update one every time you improve one or fix a bug in one, etc. It's bound to happen. Okay, and nobody's going to want to work on that code because it's so dangerous to change something somewhere. You don't know what else is going to break, you know, because of it. So we want to eliminate redundancy. So this is a classic thing with loop. If you want to eliminate redundancy, then you would put this before your test. Okay, before your loop test, because no matter what, you want to read one time a grade. If you don't read at least a grade, you don't even give a chance, you know, to the user to enter -1. So it's not an option. You cannot have really an early test loop here. You have to have a loop that actually is late test with respect to prompting the user to enter a grade. If you have an early test loop, which we had until now, you see how we had to duplicate the get statement to get it to work. So now I'm going to remove that get statement at the end, and now I have a loop that prompts the user for some data, check if we need to get out of the loop, and if not, add the data to the total and increment n by 1. And this is going to work just fine. Okay, so enter your grade between 0 and 1 inclusive, 75. Enter your grade between 0 and 100 inclusive. I think I just said 1. 100. All right, enter a grade, blah, blah, blah. I'm done for now, -1. And this is our average. Okay, so it's working. I didn't change the features, the behavior of the code. I just refactored it. I made it better, less redundancy. Now, here's a thing that I need to introduce now before we go to Java. In Java, we are going to have early test loops or late test loops. What Raptor allows us to do here is it allows us to do an hybrid. My get statement is inside the loop before the test. So it's like if I had a late test loop. However, the rest of the body of my loop is after the test, which is kind of what we do with an early test loop, right? So with Raptor, we can have an early test loop. Everything would be after the test. Or we can have a late test loop. Everything would be before the test. I'm moving right now to the segment before the test. But in addition to those two types of loop that Java also allows us to implement, Raptor allows us to very simply implement something in between, like so, where some of the code in the body of the loop is done before the test and some of the code is done after. We can do that also in Java. It's just a little less natural. Okay, Raptor makes it very easy. So that brings me to a big warning here. If you move this and this here, this code is not going to work. Why? Because you get in the loop, you read a grade. Let's say I type -1. You increment n, so n is 1. I enter the grade. Your total is -1. And then only you realize that I entered -1, which is a Sentinel, you get out of the loop. So is n equals 0? No, it's -1. So you are going to tell me that my average is -1 divided by 1. That's the average of my grade. The mistake here, and it's kind of a off by 1 mistake, the mistake here is that we took the Sentinel value as a data point, as a data value, whereas we don't want to count the Sentinel value as a grade, and we certainly don't want to add it to the total. So that's why we need to do those two steps after the test. Okay? All right, so that's a little example I wanted to take to illustrate the need to remove redundancy in loops, and that's one valid refactoring. Now, last week we talked a lot about Boolean expressions. Okay, so I'm going to try to make it a little simpler for you here, less long in time and duration. But I still want to draw your attention to this. Let's say that we are back to our guess the number game. Okay, so the guess the number game. Remember, the program figures out a random number that is actually a secret number that you have to guess. Then it asks you, give me your guess. So you type 20, and we are in a loop. The program says 20 is too small. Give me a guess. 30. 30 is too big. Give me a guess. 25. Right on. You found the solution. You guess the secret number. Congratulations, you win. Or if you keep guessing more than, let's say, 5 or 10 times, after 5 or 10 times, the program tells you you lost. Okay. So there are two things we want to test in the exit condition of that loop. One is the value guessed by the user right? Is it equal to, I should say, actually, the secret number, okay? So we can have the guess provided by the user equal to the secret number or different from the secret number, okay? So my condition would be, is the guess the same as the secret number, or is the number of attempts greater than 5? So we know, because we already talked about this example, we know that this is actually the correct Boolean expression for this problem. Okay. Now, what is interesting is when you are first designing those kind of loops, you are going to inevitably make the mistake of using OR operator instead of AND, or vice versa, AND instead of OR. Okay. So I want you to really understand how those two things differ. Okay, so if you want to get a little bit of practice here, try to do a trace with this condition and this condition. You are going to see exactly when you do the trace. That's the only way to really understand it, when you do the trace yourself. When you do the trace, you're going to really see how they differ. Okay, and that gives you a different perspective that supplement the truth table. Okay, so let me give you here the truth table that is relevant to this example here. Hold on. Let me try again to do the cut and paste like I did last time. Let's hope that it's going to be legible. It's kind of legible, so let's go with it. Okay, let's just try to improve it a bit, if I can. Yeah, okay, there we go. So we have a guess. Okay, two cases. We guess the right number, we guess the wrong number. So the number of trials that we made, we are going to say that we cannot have more than 5 attempts, okay, 5 trials. So that's our maximum number of guesses, pretty much. Okay, so first possibility, the guess is right, and I did 6 trials. So guess equals secret or equal is right is going to be true. NB trials or NB attempts, sorry, I changed the terminology there, I hope it's not too confusing. NB attempts, greater than 5 is true. Let me fix this. I don't want anybody to get confused by this. NB attempts greater than 5. Space it out a bit. Okay. Guess equal secret. I'm trying to use the same terminology that on the slide. Okay. NB attempts. All right. So that's one first possibility for this composite Boolean expression. And when I do an OR between this term and this term, the outcome is true. Okay. So if I do a logical OR between those two terms in my expression, so this would be implementing this first possibility here. This is what I get here. This is what I get when the number of attempts is 4, but I guessed right. Okay, so then this time guess right is true as well, but number of attempts being greater than 5 is false. So I still get out of the loop. Okay, I guessed. So in the first case, I get out of the loop because, well, I guessed, but I was also out of my last attempt, so that should have been called before. Here I get out of the loop because I guessed, sorry, and I was not at the end of all my possible attempts. And then same thing here, but this time I'm assuming I didn't guess, so guess equals secret is false in both cases. I have exceeded my number of attempts, and I have not guessed, and so I get out. And here I have actually not guessed right, but I have not exceeded yet my number of attempts. Well, it doesn't matter, I guess. I get out. Okay. So this is an OR statement here. You can see the table. If I take those same two terms and I do an AND statement, you can see I'm obtaining a completely different behavior. Okay. You already understood that from last week's video. If not, take a quick look, review, ask question. Okay. I'll be glad to help you with that. Now, here's what's interesting. Among the different I'm going to scroll back to the left. Among the different possible Boolean expression I showed here, I showed actually OR and AND version of using the same terms. Okay, guess equals secret and NB attempt greater than 5. And then I'm showing here OR and AND version using the negation of each of those Boolean expression. So the negation of guess is equal to secret is guess is different than secret. The negation of NB attempts is greater than 5 is NB attempts is lesser or equal to 5. So let's do real quick the truth table. Oops. Let's do real quick the truth table for those guys as well. Okay. So the table has the same structure here and it has the same flow. So I'm going to rectify them real quick here. This is NB attempts. Okay. This is guess different than secret. This is NB attempts again. There we go. And then this is doing a logical OR between both of them, and then doing a logical AND between both of them. So you see that I'm using the same test. Okay, I'm using the same value for the number of attempts, the same scenario where I did guess right or I did not guess right, and I'm trying to see what happened to that condition in all those possible scenarios. Okay, so same number of scenario, no doubt, same different expected outcome here because I'm using a different formula. So I negated both this condition and this condition, right? So when I do an OR, I get the opposite of the AND here. When I do an AND, I get the opposite of the OR. If you look at the value here, false, true, 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 that's the opposite of true, false, false, false. When I get false, 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 true, it's the opposite of true, 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 false. When you take discrete math and you do a little bit more of Boolean algebra, one of the things that you're going to learn is equivalence formula. And in this case, saying that this condition or this condition is true is the same thing as saying, and I'm going to write it down because it's a little long, okay? So saying guess equals secret or NB attempt greater than 5, okay? This is equivalent to So I'm negating the first one. Guess is different than secret. I'm switching to the opposite logical operator. I'm go from an OR to an AND. And then I do NB attempt lesser equal to 5. Okay. If I stop there, it's not equivalent. Okay. You can look it up in the truth table on the right. But then I take all of this and I negate it. Then I have an equivalence. Okay. So the purpose of this course is not to go in depth in Boolean algebra. Okay. But what I want to impart to you, like right from the start, is that when you take discrete math, a lot of students do not see necessarily the connection between discrete math and IT. Okay, they think that it's really theoretical, that there's no application. It's not true. It's actually quite fundamental. If you want to do any sort of programming, okay, and it doesn't have to be very complicated programming, the problem can start with a loop condition or an if condition that has two terms. That's it. The problem can start there. You need to be able to do what we call truth table and to assess, that it behaves the way that you want it to behave. And you need to be able sometime to figure out a different formula for your condition, for your Boolean expression that are equivalent. So when you study Boolean algebra, you are going to go through those equivalence formula, and they have a direct application on programming. That's what I want to illustrate with this example. Okay? All right, so you can see here on the right, when I negate, actually, when I do the OR of the negation of each condition, I obtain something that is the opposite of what I got with the AND here. So if I negate the OR, okay, so I do this negative condition or this negative condition, and I negate the whole thing, then I obtain the same thing then in the AND column. So those two columns, the two yellow columns are equivalent, the two green columns are equivalent. Okay? All right, and that's it for refactoring. Now debugging is going to be very short because I already covered almost all of this, through the session. So I just want to recap so that you know what belongs also in debugging. We talked a lot about off by one errors. Okay, so you can be off by one because you go you increment n by 7, and you go up to 77 when you were trying to start at 70, so probably a problem with your initialization, initialize to 1 instead of 0. You can be off by 1 because you use a lesser than instead of greater than, a lesser than instead of lesser equal sign that could cause off by 1 problem as well. So let's sum up a little bit for counter control loop does the situation. You want a counter controlled loop to iterate 5 times. Okay. Start at 0, so initialize your loop variable at 0, then test n greater equal than 5. Okay. Let's say that your loop variable is n. Okay. So initialize n to 0, then test n greater equal than 5, or start at n equal 1, same variable, n equal 1, then test n greater than 5. Okay. If you go like this, if you remember this rule, it will probably save your hide a few times, when you have off by 1 bugs. So as soon as you realize that your loops, the number of expected iteration of your loop is off by 1, these are the things I want you to start thinking of. Did I mess up my initialization? Is my initialization pretty much not aligned with my condition test? Okay. If they are not aligned, you are off by 1. So if you start at n equals 0, but you use n greater than 5 as a test, you'll be off by 1, and vice versa. Okay. So this is what I want you to start thinking about as soon as you observe an off by 1 error. Now there are different type of bugs, okay, and I think that these 4 bugs, the off by 1 bug and then the 3 bugs I'm going to briefly discuss here, I think they are the most common. So that should give you a good start here in thinking about debugging your program. The next of the common bugs with loops involve creating an infinite loop. The 3 next bugs I'm going to discuss each create an infinite loop. The first type of bug is what I would call invariant bugs. What do I mean by invariant bug? Well, let's say that I have n is assigned 0. Okay, assignment statement. Then I get into my loop, And it doesn't really matter if it's like how to say early test or late test. So I'm going to go for early test. My early test is going to be n greater equal to 10. Okay, so I want to iterate 10 times. All right, this is my decision. When this is true, I get out of my loop. Okay. When this is false, I keep going in my loop. And this is end loop. And this connects back here. Okay? What's wrong with this? Well, this one, if I give you that at the exam, I'm pretty confident like a vast majority of you will find the problem. The problem here, actually, let's see. Who can tell me what the problem is here? Maybe I'm understating the difficulty of this guy, so let's take a minute here. Think about it. No counter. Yep, that's the essence of the problem. You're absolutely right. The problem is that what I forgot here is n is incremented by 1. So that's a very specific bug. Okay. So that one you can spot just if you remember what the pattern for counter control loop looks like. Okay. If you remember the counter control loop pattern and you look at this code and you are the kind of person that is really good at playing, you know, Where's Waldo or finds the difference between two pictures, then your photographic memory is going to help you find the bug. Something is missing. All right. Now, you can also find the bug by just tracing and stuff like that, obviously, okay? But this is easier because it's so close to the pattern. Now, the general form of this bug is that you have something here in your condition. So in this case, it's n, okay? But if we had a composite, you know, Boolean expression, a multi-term Boolean expression, it could be any of the variables involved in my Boolean expression. You have something here that is never updated in the loop. So here is a potential problem. In this case, I have only one term, so it's a very big problem, okay? Because n starts at 0 in memory, okay? And I'm going to stop when n is past or equal to 10. But here's the funny thing. If I never modify n inside the body of the loop, okay, how is it going to get to 10? So that's what I call an invariant. You have something in your loop condition that should progress, that should converge toward a value or converge toward a certain property being true. Unfortunately, you never modify it, so that's it. You're going to be stuck in limbo. Okay, so that's one first example of infinite loop. Now, the second problem would be something like I'm going to use the same diagram, okay? I'm just going to clean it up a little. I start with n equals 0 again, okay? This time I'm going to add here, my incrementation statement, okay? So I'm going to say n is assign n minus 1. That's my assignment, okay? That's part of the body of the loop. That's the second type of bug. So we saw like the infinite loop due to invariance, okay? Now I'm talking about what I call infinite loop due to incrementation not converging towards the exit condition. Well, I start with n equals 0, okay? I'm going to stop where n is greater or equal to 10. So n equals 0, then I decrement it, minus 1, minus 2, minus 3. So here's our number line, okay? This is where I need n to be to stop the loop. N starts here at 0, and n is going as fast as it can, you know, in the opposite direction. So you make a mistake with a +1 instead of a -1 at an incrementation step. Even for your initialization is good and your loop condition is good, that's going to create an infinite loop. That's the second way, classic common way to create an infinite loop. What about the third one? Due to exit condition being too strict. What do I mean by that? We already saw that one. Let me again modify the diagram. Okay. We talked about that one. I'm going to fix this. So I'm going to get n plus 1 here. Actually, I'm not going to use n plus 1. I'm going to use n plus 7. So we had n initialized to 1 here. Okay. And I think we are using 70 here, okay? Alright, but instead of doing greater or equal to 70, I'm going to be a little bit too narrow. Let me rewrite this. I'm going to be a little bit too narrow, and I'm going to say my exit condition is n equals 70. So you remember, huh? You remember what happened there? We kind of went through it during tracing. So what's happening is that I'm way too specific here, okay? If this was n greater or equal to 70, it would work. Because I just test n equal to 70, my n value is going to start at 1, then it's going to be 8, then it's going to be 15, then it's going to be 22, 29, 36, 40, 41, 48, did I mess that up? 52, 59, 66, 70, I think I messed that up, but no matter. It's still, it's a bad example that still makes the point, okay? By incrementing like that, I'm just going from being below 70 to being over 70, so I have never a chance to trigger my loop exit condition, okay? So that would be what happens when your exit condition is going to be too strict. It's possible that originally when you wrote this program, you were incrementing by 1. So you just said, you know, n equals 70 is a good exit condition. Or you were starting with n equals 0, and n equals 70 was a good exit condition. So it's not that testing equality is bad, it's intrinsically bad. It's just that it's brittle because it's highly dependent on your initialization and of your incrementation. So we always go back to the same three things, right, with loop. We talk about initialization, at least with counter control loop. We talk about initialization, we talk about the condition, and we talk about the incrementation. Every time you have a problem with a counter control loop, most likely your problem comes from one of those three failures, okay? One of those 3 points in the program. All right. And I think I'm done with everything I wanted to cover for debugging. So it took us about 1 hour, 45 minutes to go over this. I hope this was useful information. I hope that helped connect, you know, the content of the module to actually the 5 different programming skills and actually the question of the exam. That's also the point of those weekly live sessions. I'm going to open the floor for a few seconds, Dave, waiting for somebody to type a question. If you have any question, let me know. If you don't mind it being recorded. Other than that, if I don't see anybody typing as I do usually, I will just close the session. And then I will hang around a little bit in case there are questions that you wanted to have off recording. Okay. So I don't see anybody typing right now. So I'm going to thank everybody who was able to attend. We had actually the session moved by 1 day, so that might have caused problem for people who set aside Monday night, you know, to attend the session, and I apologize for this. But I'm glad that at least some of you were capable to attend. So thank you for coming and patiently sitting through the entire session and participating. And then everybody else who's going to watch this recording as a video that you download, don't hesitate to get in touch with me to post questions on the forum if anything is unclear, okay? It's not because you didn't attend the session live that you cannot ask a question. It's just that we're going to do it by forum pretty much. So don't hesitate to ask any question you have. And just as a reminder, you have an exam this week that has been released by our TA. Exams are personal work only, so you cannot ask for help to anyone but the TA and myself. Okay, so if you have any question about the exam, or generally speaking anything graded in this course, you send an email in the case of the exam to the TA and copy to me. Okay, and one of us will get back to you as soon as possible with clarification or anything that helps you address your question. But this is a rule: personal work only, and you cannot ask a question about a graded assignment to anybody but the instructor and the TA. Okay. All right, thank you again for attending, for watching this video, and I will stop the recording for tonight. Have a good night, everyone.